Hello everyone, thank you all for attending this presentation. I am Giovanni, I am a postdoc at University of Toronto, and I am going to talk to you about how to represent and solve quadratic optimization problems with Gaussian Boson sampling. The last decades have seen the emergence of many quantum computing models, each of them with singular properties that can be with more or less difficulty simulated by classical computing. The quantum annealing models has seen a growing interest from the optimization community for a couple of years now, as it has been proven very efficient at solving quadratic unconstrained binary optimization problems. However, in our work we are interested in photonic quantum computing, and especially the Gaussian Boson sampling model, which consists in manipulating photon states by passing them through a network of quantum gates. This presentation is then about how to use GBS properties to represent and solve optimization problems. The plan of this talk is the following. I will first define Gaussian Boson sampling, then I will show how to use Gaussian Boson sampling to solve quadratic knapsack problems as a first use case, and then I will present you an attempt of generalizing the approach to any Cubo problems. Gaussian Boson sampling consists in passing photons through a quantum gates network called linear interferometer and observing the output configuration on various photon detectors. Actually, the linear interferometer is entirely determined by a matrix of coefficients, equivalently a weighted graph, that determines the relation among every Q mode. So another way of representing GBS is to consider a graph as an input, and you can imagine there is a light bulb on every node, and then you push a sampling button, and some light bulb will light up, some won't, and the output configuration will give you a subgraph. So to summarize, GBS is a tool to sample subgraph. But what kind of subgraph does it sample? So there is a probability law that is given in the formula here. And so basically the probability law, the probability of sampling a subgraph S is proportional to the affine of its adjacency matrix. That is, the probability of sampling S is proportional to the number of perfect matching in S. And computing the number of perfect matching in a graph is a sharply complete problem. And this is why simulating the behavior of GBS with classical computing is intractable for large graphs. Also, something that we know is that the number of perfect matching is highly correlated with the density of the graph. Therefore, GBS is a tool to sample dense subgraphs with high probability. Actually, this can be extended to weighted density. So in this graph here, the subgraph in red has a higher probability to be sampled than the subgraph in the lower left part, even though the edge density is lower. In the following, when I will talk about density, I will actually refer to this weighted density. So there is another parameter that influences GBS, is that we can set the number of photons detected in average. That is, the average size of the sampled subgraph. Those red subgraphs in example is what GBS would return if we set mean photon numbers equals to 5. So if one wants to find the densest subgraph of size 5 using GBS, then the mean photon number should be set to 5. With all these interesting properties, it is easy to imagine how GBS could be useful to solve some classical graph problems. This work shown here focused on identify densest subgraphs, identify maximum clicks, and solving clustering problems. And in our work, we go one step towards representing more general optimization problems with Gaussian Boson sampling. So our first use case is the quadratic knapsack problem, because it is a simple problem to state with very easy constraints, and I think it suits well the use of GBS. The quadratic knapsack problem consists in selecting a subset of items among n items and put them in a knapsack. Each item I has a weight Wi, and the knapsack has a capacity C. Each item has a profit Pi, and also each pair of items ij has a profit Pij, which is what makes it different from the standard knapsack problem. The objective is then to maximize the total profit of the selected items such that the knapsack capacity is respected. More formally, if we have a variable xi for each item, which is equal to 1 if item I is selected, then we want to maximize the quadratic term xpx, where p is the profit matrix, such that Wx is inferior or equals to C, which is the capacity constraint. To get more intuition on what we are going to do, I'm going to use a graph representation of quadratic knapsack. So we have one node per item, and each edge ij are labeled with profit pij. And we have also a profit pi on each node. Actually, the adjacency matrix of this graph is exactly the profit matrix of our problem. The reason why we use this graph representation is because the solution's profit is directly related to the density of the corresponding subgraph. Then it would be very tempting to use GBS on the profit matrix to sample solution for the quadratic knapsack problem. However, the problem is that identifying dense subgraph will not necessarily give solution that respects the capacity constraint, so we cannot use GBS directly on the profit matrix. For this reason, we need to modify the profit matrix to include some information on our capacity constraint. This is why we introduce the utility matrix, in which we are dividing each profit by the cost in weight that is required for selecting these items. The intuition is that using GBS and the utility matrix will bias GBS towards solutions that respect the capacity constraint. However, and unfortunately, this is not enough to ensure that the return sample satisfies the capacity constraint. And even more, return samples could be incomplete, in the sense that we could actually add more items to the solution. This is why we need fixing algorithms. So we have tried 3 different greedy fixing methods. The first one is based on local profit improvement. We are selecting items according to the profit and the items already selected in S. The second one is based on local utility improvement. We are selecting items based on the profits, potential profits, and weights, without considering the items already selected. The classic greedy approach for solving the knapsack problem is actually based on this utility improvement. And the third one is a combination of the two above. We are selecting the items according to some local utility improvement measure. And so the whole method for solving a quadratic knapsack problem is a 3-stage method that I've called the sample and fix method. So we are generating a large number of samples, and for each sample we apply our greedy fix method, which is if the solution is not respecting the capacity constraint, then we remove items according to their local utility or profit, depending on which greedy fixing method you use, and we do that until the capacity constraint is respected. And then we try to add items if it's possible until no more items can be added. In the end, we simply return the best solution. So we have run a few experiments on 100 randomly generated instances. Each instance has n equal 18 items, and we have compared 3 different sampling methods. First one is GBS on utility matrix, the second was in GBS on profit matrix, and the last one is random sampling, in which each item has a 0.5 probability to be selected. For each instance, we generate 100 samples with each sampling method. We set the mean photon number parameter to the expected number of items that is needed to fill the knapsack, which is the capacity C divided by the average weight of item. For each sampling method, we also compare our 3 greedy fixing methods. And what we are interested in is for each combination of sampling and fixing method to look at the mean objective over the 100 samples, the median objective, the maximum objective that is reached, and the number of optimal solutions found. Also, we are not going to use the real photonic quantum hardware for this experiment. During this study, we had access to one photonic quantum chip from Xanadu, but the size of the chip and its architecture were too much constrained to show any interesting things for our problem. Instead, we use a simulation of GBS thanks to the Strawberry Fields API, also developed by Xanadu. We can simulate GBS for graph of size inferior to 30. Above this limit, it becomes intractable. So here are the results we got. Each curve corresponds to a combination of sampling and fixing method. And for each combination of methods, we have sorted in ascending order the measures we got over the 100 instances, and we have normalized it regarding the optimal solution. So we can compare the overall efficiency of each approach. What we can conclude from this experiment is that using GBS and the utility matrix is the best approach to sample interesting solutions. And also using the greedy fix algorithm based on local utility improvements gives the best solution among all greedy fix methods. So we just showed that GBS is able to capture promising subset of items for the quadratic knapsack problem. However, for the size of the instances that we just tested, classical methods like MIQP, for example, can solve problems to optimality very quickly. And unfortunately, we cannot conclude on the ability of GBS to outperform classical approaches for the quadratic knapsack problem. Even though current photonic quantum chips of the simulation are too restricted in terms of size of problem we can solve, we think it's still interesting from a theoretical point of view to extend this study to other optimization problems. And for that, we will use the Cubo angle. Cubo stands for Quadratic Unconstrained Binary Optimization, and the objective is to maximize a quadratic term xqx, where x are binary variables. And also there is no constraint. This formulation is actually very generic, and almost every optimization problem can be exploited as Cubo. So let's take an example with the traveling salesman problem. So we use a rank-based model, and our variables are xip, and it is equal to 1 if city I is visited in position p in the sequence. Then the term dij times xip times xgp plus 1 is the distance between I and j if j is visited right after I. So we can express the xbt function as written here in the model, and the term on the right represents the distance between the last city and the first city visited, as we need to go back to the original city in the TSP. And our two constraints simply state that every city must be visited once and every position is filled once. If we want to transform this model into a Cubo model, we need to relax these constraints and add them as penalties directly in the objective. For that, we need a penalty coefficient alpha that is sufficiently large enough to make sure infeasible solution can't be optimal. And so we can model many optimization problems as a Cubo model like this. And usually to solve Cubo, we can use classical solver like Gurobi. Also, there are many works on table search and simulated annealing, and more recently quantum annealing. And also specialized hardware like digital annealer, which take advantage of intense parallelization to solve Cubo problem. And we are going to try to solve Cubo problems with GBS. So first, the intuition is almost the same as for the quadratic knapsack problem. That is, finding x that maximizes the quadratic term xqx is the same as finding the densest submatrix of Q. And this sounds really good because this is exactly what GBS could do. Unfortunately, this won't work. And the reason of that is Cubo matrix has negative and positive entries. And in that specific case, the affine operator is much less correlated with the graph density. Here is an example, in which the upper left coefficients are negative but have much higher absolute value. And I won't get into the affine value computation details, but it is very similar to computing the determinant of a matrix. It is a sum of multiplication of coefficients. And in this example, using GBS would return a very bad solution for the Cubo problem. So we cannot directly use GBS on the Cubo matrix to identify promising solution. So we had a simple idea. What if we add a sufficiently large constant k to each coefficient of the Cubo matrix, such that every coefficient in this new matrix Q prime is positive? The idea is that we can use GBS on this new matrix Q prime to find solutions that maximize the quadratic term xq prime x. But what does it tell us about the original Cubo problem? Because clearly solving both problems is not the same. If every coefficient is positive, then the optimal solution is simply to assign every variable to 1. However, we can add one constraint to make both Cubo problems equivalent. And this constraint is the sum of every variable xk is a constant c. Actually, this constraint is often implicit and met for many Cubo problems. So if our Cubo problem meets this condition, we can use GBS on Q prime to identify promising solution of the original problem. And this is the case for our Cubo formulation of TSP. Indeed, we have a variable xip for each city I and each position p, and we want each city to be visited once. So the sum over xip have to be equal to the number of cities. So in theory, we can use GBS to find solution of TSP, and we have run a few experiments on 4 random instances of TSP. So these instances are very small with n equals 4 cities. This is because the size of the Cubo matrix is quadratic regarding the number of cities, and larger problems would be too large for using GBS. So for each instance, we generate 100 samples and we compute the objective, which is a quadratic term xqx, and we sort the objective in descending order and show the profile of solution. So in blue, this is the results we got for GBS, and in red, this is the result we got for random sampling. Some objective values are very high because the solution corresponds to infeasible solution, and in Cubo problems, violating constraints is penalized in the objective function. We also looked at the number of samples that reach optimal solution and number of samples that reach feasible solution. And what this experiment shows is that GBS and random sampling have equivalent behavior, which means they are both very bad at identifying promising solutions. Our hypothesis for these bad results is that the coefficient distribution in Q prime is very bad for GBS to sample interesting solutions. It is actually hard to know what would be a good matrix distribution for GBS, but we think that maybe the problem comes from how constraints are added as penalties into the Cubo matrix. In our first use case with Quadratic Knapsack, we managed to bias GBS towards feasible solutions thanks to the utility matrix. But it is an open question to know how to extend this to any Cubo problems. So in this talk, we have presented the first approach to the best of our knowledge for representing and solving constraint quadratic optimization problem with a photonic quantum computing model. Unfortunately, current hardware size and simulation are too restricted to show any advantage of using GBS over classical methods for solving quadratic optimization problems. And finally, we have tried to extend our study to many more constraint optimization problems through the scope of Cubo formulation. However, it is unclear how to represent constraints inside Cubo matrix to make it relevant to the use of GBS. That's all for me. Thank you all for your attention.